Hello everyone, today I'm presenting our supervised machine learning network intrusion detection system built using this dataset right here, the CIC-IDS2017 dataset. As a cybersecurity analyst for a financial institution processing millions of daily networking, it is impossible to track every single person individually manually. Our current problem is we're getting DDoS attacks or denial of service, a brute force attempt to make people unable to use our system or network. Our objective is to build an automated deep learning network that suggests raw information like traffic network and classifies them in real time, either being normal traffic or malicious traffic or DDoS attacks on our project. To train this data set, we use a real-world data set, which I've stated previously, which is this. This data set might have several real-world challenges. There's a lot more normal days than there are days where there are cyber attacks. The next issue might be we have a lot of the same data over a couple of days, so we might have duplicate files or files that have errors in there, like if there's nothing in the file itself, or where there's supposed to be something. With the rough draft of what our project needs, we're going to transition over to the Google Colab and see how we handle these things. In code block 1 and 2, as you can see, we loaded all the basic information we needed. We loaded pandas and all the other things we need to process this information, as well as all the datasets we'll need. We'll load others later. Those are purely for immediate use. This removes any duplicate files or anything that might have it drops duplicate files, and also anything that might not just be there or information we can't use. With all the basic stuff out of the way, we move down to block 3. This allows us to target the information we want, and it drops out what we are trying to target so we can train the dataset. This also specifies what we're trying to do. 0 is what we normally want, for a 1 is what we consider attack against the system. In code block 4, we split the training set into multiple areas. We performed an 80-20 training test split. Currently, we fit our standard scale not only on the training set, but for the test set. Scaling normalizes the features of the data, making sure the data set has no data leaks, or we standardized data, so everything in the data is of similar or equal quality. So if there's inches and feet, it will all be considered inches, and the feet will be considered reconverted into inches, so the data set can not have to shuffle around using different numbers that can mean the exact same thing. In code block 5, this is the setup for the actual training model. As you can see, the model has 16 neural network points for the top one. Then the second hidden layer will have 8. Then the last hidden layer will have stigmoids, which will determine if it is one or the other. or 0 or 1. This what allows us to see if it is actually happening, if we're getting attacked or not. Here's are the things we use to actually train the thing. An epoch is how much it will do the thing, how many times it will train the dataset. It'll train a dataset 100 times with a variable of 0.1. We could set this a bit higher so we can get more accurate information, although for time constraints I have not done this. And that's the basic setup for all the information for the model. In code block 6 through 10, it just roughly shows us the results of the actual AI, or deep learning model. It scored rather well on average. Got 57, 99, and another 99. On the average day of Wednesday and Monday, it scored in 99 as well. Now our model is not the best, admittedly so. It scores not a lot of false positives, but it does score a few. In cybersecurity, we call this one of our most critical metrics. A false positive is a minor inconvenience for analysis review. A false alert, but a false negative allows an attack to breach networks defenses unnoticed. Our model demonstrates strong classification accuracy on internal test splits and generates expectantly well to external threats as well, like port scan, which I know it's up here. It's Wednesday, port scan. As you can see, it did score pretty well. It got a 75. To combat data drift across novel attack signatures, we recommend, at least I recommend, lowering the percentage on the training thing, which is right here, to be 0.5 or down to 0.3 or 0.5. This could improve the numbers down there, but this one took like 6 hours. Sorry, that's an exaggeration. It took roughly an hour for this one to complete. I think I was just on a bad day, so it took a while to load, so I didn't want to increase it. Although it would have increased accuracy if I decrease this number to 0.5 or lower, or somewhere around that mark. It could have increased the accuracy, allowing us to get more accurate results. I do recognize this, but I chose not to do it because it was taking too long to load each time. In conclusion, this deep neural network pipeline provides fast millisecond interfaces to filter out millions of daily consumer use, ensuring securing the operating center for analysis to focus their time on genuine threats. Thank you for listening. This is the completed thing. Hooray!